Known for two things, and that's space and dinosaurs. And there's one unifying tie between the two. 66 million years ago, there's very strong evidence that a giant asteroid hit the Earth and caused a mass amount of change on this planet, which led to the extinction of the dinosaurs. How do we know that happened? Well, in the 1980s, a geologist named Walter Alvarez uncovered, with the help, actually, of his physicist, Nobel Prize-winning father, that right at the PG boundary, which was the point of dinosaurs' extinction, you had a particularly strong amount of what's called iridium. And iridium, which is atomic number 77 on your periodic table, is mostly found in high quantities in asteroids. In the Earth, we can find it, but it's locked further down in the Earth. When you find a lot of iridium, that's a bit of a smoking gun that you've got the signature of an asteroid impact. So the theory was put out there that an asteroid impact was the reason that the dinosaurs were extinct. So if something hits, you would expect there to be a crater. Now, around the same time that the theory was put out there, there were oil exploration surveys that were ongoing in the Yucatan Peninsula. By chance, they uncovered what's now called the Chicxulub Impact Basin, which is the right size and had the right chemical composition around it, that we think that that is the site of the giant impact that led to the extinction of the dinosaurs. The thing is that asteroids or parts of asteroids, dust of an asteroid, we actually get hit by it all the time. Anytime you see a shooting star, you're seeing a bit of a piece of rock that's burning up in your atmosphere. The ones that we worry about are the big ones. The one that knocked out the dinosaurs was 6 miles in diameter. That kind of impact, it happens, but it's far more rare. And unlike the dinosaurs, astronomers are ready and watching for one that might be hazardous.
Did an asteroid kill dinosaurs? Paleontologists agree that an asteroid did strike Earth at the end of the Cretaceous period at around 66 million years ago. And we know this because there is an impact crater in the Yucatan Peninsula of what's now Mexico. And the rock layers from that age include an element called iridium, which is rare on Earth, but relatively abundant on asteroids. And you can learn more about the asteroid itself by clicking the link here. It obviously had drastic impact on life forms on Earth, including dinosaurs like T-Rex and Triceratops. So because the asteroid was really big, the impact would have had global consequences, both immediate and then also long-term. There would have been initial effects like forest fires and giant tsunamis, but the projectiles that came off the impact would have led to impact winters, which would have cooled down the Earth and also blocked sunlight from hitting the ground. And the vegetation would have suffered, which would have led to the collapse of a lot of ecosystems. So it's very clear that the asteroid impact had a major effect on life on Earth. But what we're trying to figure out is whether the asteroid was the only factor or the major factor that led to the extinction of dinosaurs. Some paleontologists have proposed that the dinosaurs were already on a decline before the impact of the asteroid. But this hypothesis is difficult to prove just because we don't have a clean, complete record of dinosaurs right before, during, and right after the extinction event. So it's hard to tell whether all the dinosaurs were already on the path to extinction, even without help from the asteroid impact. There's also evidence of increase in volcanic activity at that time. There was a lot of lava and volcanic particles spewing out from underground, and this would have led to similar effects as the impact winters. So the increase in volcanism might have contributed additional forces that led to the extinction of dinosaurs. It's not all doom and gloom, though. One dinosaur group we know as birds did survive through the extinction event, and also us mammals did as well. What the fossil record tells us is that certain animals, usually smaller bodied, and also those that lived in the oceans, tended to fare better at this extinction event. So all the animals that are alive today represent descendants from a group that actually did survive this asteroid impact. So to answer the original question, the asteroid impact did have a devastating effect on the dinosaurs, but paleontologists are still working out the finer details. And learning more about this extinction event could help us understand other extinction events, including the one that we're facing right now.
When will the sun die? Stars don't actually die, but rather they just morph into something else. And how long that takes really depends on how much hydrogen they have and how efficient they are at burning that hydrogen. In the case of a star like our own sun, we can figure that part out by looking at it and seeing how bright it appears in the sky, and then measuring how far away it is. And when you put those two things together, what you discover is that our sun is sort of a run-of-the-mill, medium-sized, G-type star, and these stars tend to live for roughly 9 to 10 billion years. But to find out how much time the sun has left, you need to know how old it is now. And you can't just ask the sun how old it is. So what astronomers and geologists do is we turn to the rocks of the solar system, and specifically the best kinds for age dating the solar system are meteorites. And those give us an indication that the solar system is about 4.5 billion years old. So when you take that into account with the fact that the sun will live for about 10 billion years, we know we've got 4.5 to 5.5 billion years of fuel left in the sun. But what happens when the sun starts to run out of fuel? Up until this point, the sun has been relatively stable with a very nice balance between two forces. There's the inward force of gravity, which is trying to force the sun together, and the outward force of radiation pressure, which is pushing outward due to reactions that are going on at the core of the sun. And as the sun dies, as it's running out of fuel, you start to lose that balance. And initially, radiation pressure decreases, and the sun starts to collapse in on itself, decreasing and shrinking in size. And when that happens, the core of the sun actually gets hotter. You get another phase of burning, and the sun starts to expand again. And the sun will move into this phase that we call the red giant phase, which will encompass Mercury and Venus and spread all the way out to where the Earth is right now. Ultimately, there's just not enough fuel to sustain it, and so gravity collapses the sun down to a fraction of its size, of its temperature, of its brightness, and turns it into this object that we call a white dwarf that's really dense and has a strong gravitational field. But it's faint and would not be visible to the human eye. Everyone wants to know how much longer the sun has to go, because without a sun, it really means big trouble for the Earth and for life on Earth. But you don't have to worry, because we've got plenty of time. Hopefully, we'll be out exploring the cosmos and looking for new worlds by the time the sun runs out of fuel.
How long did T-Rex live? T-Rex is not only the most popular dinosaur, it's also the best studied. So we know that T-Rex lived up to about 30 years old. Smaller dinosaurs like Velociraptor lived up to about 20, 25 years old, and gigantic long-necked sauropod dinosaurs lived to about 70 or even 100 years old. And T-Rex sits right in between in terms of both size and lifespan. So just like the animals that live today, size did matter in terms of how long you lived. How do we go about finding the age of these dinosaurs? Dinosaur fossils have growth rings, much like tree rings. And so you can count the number of these lines and roughly estimate the age of the dinosaur when it died. We can also find out how the dinosaur grew during its lifetime by measuring the amount of bone between these lines. The greater the distance, the dinosaur grew more quickly, and the shorter the distance, the dinosaur's growth slowed. From looking at different T-Rex bones, we can create the life history of T-Rex. T-Rex started out small and weighed about 30 kilograms, or just over 60 pounds when it was 2 years old. And it steadily grew until its early teen years, up to about 2,000 kilograms, or 4,500 pounds, which is about the weight of a rhino. While we have this strong image of an adult T-Rex chomping on large herbivorous dinosaurs, juvenile T-Rexes were much smaller, they had much lower bite force, and they were more agile. So we believe they fed on more moderately sized animals. And at this point, T-Rex went through a massive growth spurt during its teenage years, from about age 13 all the way to about 20 years old, much like humans. But unlike humans, T-Rexes grew up to 2 kilograms, not per year, per month, or per week, but per day. And then T-Rex reached its adult size around the age of 20, where it reached an astonishing weight of 6,000 kilograms, or over 13,000 pounds, which is about the same weight as an African elephant. Once it reached its adult size, T-Rex didn't grow much bigger or even much older. The oldest known T-Rex is Sue, which was 28 years old. And this is a larger trend in dinosaurs, where we only tend to find young or young adult fossils and not many fully grown adults. And so we think that dinosaurs lived fast and died young. Although we're just left with the bones of T-Rex, as you can see, we can learn much more than just its anatomy. And you can bet that with new fossils and new technologies, we'll learn even more about the lives of these dinosaurs.
Is there life in the universe? There are two ways to answer that question. One is via science. You try and quantify anything that goes into that question. The other is your gut. We'll get to that one at the end. For the scientific way, we can really thank an astronomer named Frank Drake, who came up with an equation in the 1960s that attempts to give a quantifiable approach to answer this question. And Drake's equation has a number of pieces that go into it to give you a number at the end of how many planets might you expect intelligent life to exist on. One piece that's pretty basic is how many stars are there in the galaxy? How many of those stars have planets around them? How many of those planets are in the habitable zone of their star? And then it gets a little bit more complicated into things that we're not quite sure how to answer. How often does microbial life sprout up on a planet? And then how often does intelligent life emerge from that? You can get an answer that's as small as just the Earth, or as large as hundreds of thousands, if not millions, of planets in our own galaxy that might have intelligent life on them.
And that kind of range from basically nothing to everything means we don't have enough information to confidently say one way or another.
Drake's equation is definitely one way that you can go about trying to get to the answer. But I just don't think that you're going to have a pen and paper answer to, is there life in the universe? I actually think it's going to come about because of a discovery. That's why I turn to my gut for the answer to this question. I see life everywhere on this planet. I feel strongly that the oceans of Enceladus and Europa are going to end up having microbial life or some sort of life in them. And so my natural answer is yes. There is life out there in the universe. But if a discovery doesn't happen in my lifetime, I'm not going to count it as nil, because the lack of a discovery doesn't mean that it doesn't exist. Astronomers certainly won't stop looking. This will always be a question that we seek to have an answer to.
Are dinosaurs still alive today? The remarkable answer is that dinosaurs are still alive, but you don't need to go looking for them on some deserted island. They're actually all around us because all birds are dinosaurs. Not only did birds evolve from dinosaurs, scientifically they are dinosaurs, just like how us humans are primates. 66 million years ago, an asteroid impact did kill off a lot of the dinosaurs, but one lineage survived, and those are the ancestors of all modern birds. To this day, paleontologists have never found a non-bird dinosaur that was alive after the extinction event. Even if we did, we would be too excited to keep it to ourselves. Now that we know birds are dinosaurs, some of you might be disappointed that modern dinosaurs that are alive today don't really look like the dinosaurs from the Mesozoic era. But new research is finding that dinosaurs had a lot of the important features we associate with birds today. For example, we now know that many of the dinosaur groups had feathers or precursors to feathers we call protofeathers. Because these dinosaurs clearly didn't fly, we think that feathers first evolved for regulating body heat or for display. Dinosaurs, like birds, already had high metabolisms, hollow bones that made them lighter, wishbones, and also relatively large brains for their body size. So collectively, dinosaurs may have looked a lot like birds, and if you were dropped off in an environment in the Mesozoic era, you might actually mistake some of the dinosaurs for turkeys. The next time you see a humble pigeon, just remember the fact that they're part of a very successful lineage that survived the mass extinction event 66 million years ago that wiped out all the other dinosaur groups.
How do we find new planets? So we've known about planets like Mercury, Venus, Mars, Jupiter, and Saturn as long as we've been looking up, as they were obvious objects in the nighttime sky. Bright objects that move different than the stars do. And the way that I can say that we detected them would be with your eye or with direct imaging. So you've directly detected those planets. In today's world, we're searching for planets around other stars, objects that we call exoplanets. And this direct imaging method is actually something that we try as well, just with far more complicated instrumentation. So we haven't found that many planets that way. But there are other methods that astronomers use as well. One of the most popular and productive is called the transiting method. You can see the light of a star dip ever so slightly in a cyclic pattern due to a planet moving in front of it from Earth's perspective. So we watch thousands upon thousands of other stars, and we look for tiny dips in the light. Thousands of planets have been found that way. Other methods take advantage of something called the wobble. If you have a big planet around a decent-sized star, the planet will tug on the star, causing it to wobble a little bit. So one way that you can see that wobble is through what we call the radial velocity method. And this is where you take the light of a star and you break it up into its fingerprint. And you can see that light fingerprint move towards you or away from you, depending on if the planet is tugging the star towards you or away from you. Similar to the Doppler effect, where when a car is coming towards you, the sound is higher, and when the car is pulling away from you, it's lower. And the other way you could take advantage of that wobble is something called the astrometric method. And that's where you would very, very carefully watch the position of a star, and you could actually see it jump back and forth due to a planet pulling it towards you or away from you. And while we have yet to discover a planet using this method, there are new catalogs and surveys that will allow us to detect planets this way. We now know of thousands of exoplanets orbiting other stars, and the next generation of telescopes is only going to give us more information and more planets. And we will soon be able to tell far more stories about the diversity of exoplanets in the galaxy.
How do you find dinosaur fossils? Discovering a dinosaur fossil is one of the most exciting part of being a paleontologist, but it also takes a lot of preparation and hard work. So the first step is for the paleontologist to figure out where to dig for fossils. The region has to include sedimentary rock layers like limestone or sandstone, because those are the rocks that contain fossils. These sedimentary rock layers need to be exposed on the surface so that the fossil bones are on the ground where paleontologists could easily pick them out. The sedimentary rock layers need to have been formed while dinosaurs were alive, so that would be between about 230 to 66 million years ago. So if a region ticks all these three boxes, then there's a good chance that you'll find some dinosaur bones in the area. So once you made the decision on where to look for fossils, then it's time to actually start your field work. The first phase is called prospecting, where all of us would just stare at the ground for miles and miles and hours until we find fragments of bone on the ground. And we walk with this magnificent tool called the rock hammer. So when we do find fragments of bone sticking out of the ground, then we can use it to either take it out of the ground and also to dig a little further to see if there are any other bones nearby. A lot of people might think that when you're looking for fossils, you might see whole skeletons, but typically what you find are fragments and very damaged pieces of bone, like this one here. So one of the important skills for paleontologists is to be able to tell apart fossil bone from regular rocks. And so we look for features like grain texture on the surface, and also internally there should be holes where blood vessels and bone cells used to be. Paleontologists can learn a lot from just little bits of bone. We can learn about how the dinosaur grew or what the overall size was. And in a lot of cases, we can tell to which group these fossils belong to. So this is a piece of bone from a duck-billed dinosaur. Once you find some dinosaur fossils, then you're ready to move on to the next phase of fieldwork, which is called excavation. And this is where you dig out the fossil bones. But at this point, you are not interested in taking out the bones individually, because a lot of the fossil bones will be fragile. You'll be taking out the bones with the surrounding sediment and then shipping it to a lab so that you can prepare it using specialized tools. So the steps involved in fieldwork hasn't really changed in over a century, although a lot of the techniques for analyzing dinosaur bones have changed quite a bit, even in the last decade. And finding fossils still takes dedication and determination, a little bit of luck, and also knowing what to look for. Right now, there are paleontologists digging up dinosaur bones on all 7 continents. And so this might make some people worried that there will be a shortage of dinosaur fossils in the future. But we're finding more and more fossils, and there is no sign of it slowing down. For me, it's the best part of being a dinosaur paleontologist.
Poor Pluto was reclassified from planet to dwarf planet in 2006 when the International Astronomical Union voted on a new definition for the word planet that unfortunately no longer included Pluto. So when that happened, we went from having 9 official planets to 8. The definition of the word planet was not really well defined. And Pluto was always just a little bit of an oddball. It's smaller than our own moon. It's got a very different kind of orbit than the other planets in the solar system do. Astronomy had moved so far forward since the year 1930 when Pluto was discovered to the current times in 2006 that astronomers decided they needed a new definition. So the definition has 3 components to it. The first is that it needs to be in orbit around the sun. Pluto's okay with that. The second is that it has to be massive enough to be nearly round. Pluto's okay with that one. And the third component was that it needs to have cleared its orbit of objects. And this is where Pluto fails. A quote-unquote planet would be massive enough to control any other object in its orbit with its gravitational force. Pluto happens to be in this belt of debris, so Pluto isn't the only dominating force in the area, and it certainly isn't the regulator of how everything else moves. People were very attached to Pluto being called a planet. The public outcry really surprised astronomers because the objects we study don't care if you call them planets or not. It doesn't bring anything scientifically to the table, and it means that we don't pay as much attention to the objects in our solar system that aren't under that umbrella of being called a planet. When we hear the word planet, we think exciting, life. When you hear the word moon, you may think of a dead place, but Enceladus is a moon around Saturn that is probably the next best place to search for life. So the word planet is certainly not all-encompassing of the different kinds of objects that are out there. I argue that we should just get rid of using this word planet. A word that I am trying to get more people into is world, because world is far more inclusive and gives equal weight to all the kinds of exciting objects that we have in the solar system.
Many people think that pterosaurs are dinosaurs because they're reptiles and they lived at the same time as dinosaurs. But pterosaurs are not actually dinosaurs in the scientific sense. So when we call something a dinosaur, we mean that it belongs to the group Dinosauria, which was named by Sir Richard Owen in 1842. And within Dinosauria, there's three main groups. You have the ornithischian dinosaurs, like Triceratops and Stegosaurus, and you have the long-necked sauropod dinosaurs,